Hello, smart people. So I'm really excited. So because this is our now 17th lecture on these tensors, and we have already talked about this affine connection. And today's topic is again I'm basically repeating this lecture, and we need to discuss something more because in the previous topic we have already talked about that. If you take the variation of that, if you make that take the variation of some vector of or a tensor, you can say that of some rank. Suppose you have some tensor of rank 1. If you make its transformation, so the transform vector, so you are getting some new tensor but of same rank, right? But the story is different because if you talk about this flat space or some curved space, the story is different because when you talk about, because we are working in the 3 to 4 dimensional this space time, this Minkowski space, I mean to say. So there basically I'm not getting exactly some, if you take variation of some tensor or a vector, I'm not getting the some another vector or tensor but of same rank. I'm getting some additional terms. So this we have already discussed, right? So this basically we get this extra stuff that is basically about that this affine connection. It basically relates that if you talk about the free fall of a book, so you have a book and you are releasing it and it moves it moves under the effect of the gravitation, and we neglect the force of this the force due to the resistance of air, you can say that, right? Now, so what basically this I'm revising it. So, or you want, you can visit my this previous videos, previous lectures on these tensors. So that there we have discussed about the spin connection basically relates the two coordinate systems, because if you talk about the free fall of a book, the coordinate, the four vector, or you can add the four displacement of that book. It is basically how you can relate it with the four vector of this something which is with respect to the earth, right? So this is how to connect these two coordinates, right? So this is basically given by this what is called affine connection, right? So we have already talked about this. This is basically an affine connection. This term I'm getting now. I already add one more point here. If you talk about that, if you say that the signs are equal, or if you talk about these indices are equal, right? So in that case, this term should be equal to that that lambda prime mu nu, right? So that means it basically transforms like a tensor, right? So as I already told you, if you talk about that whether this affine connection is a tensor or not, so in general it is not a tensor, right? But if you talk about the first term, so it clearly seems to be that if the indices will be equal, so it basically superimposes the whole physics, right? Because I am getting that this affine connection is a tensor then, right? So that means, but because of the second term that's present here, so we have the second term. So because of the second term, it basically prevents it from transforming like a tensor, you can say, right? So it basically helps us, right? Now, if you rewrite that, so if you rewrite the first second term, so if you rewrite the second term, that's partial x prime lambda. So that can be equal to, right? So what I do here, I simply, तो यहाँ पे मैंने क्या किया, I basically split the second term, that is partial to x rho by partial x prime mu, partial x prime mu. I basically wrote it as a combination of two terms, product of two terms, right? So this is first I write the mu in new indices and mu indices, right? So rest is same. So if you have a look on this term, so this is basically if you write that partial x prime. Okay. So this is very clear because when lambda equal to nu, so this term, because so you get that partial x prime lambda by partial x this rho this partial this, so this whole term will cancel, so it should be equal to when lambda equal to nu, because this delta lambda nu, it is simply that canonical delta, and its value is equal to 1 if the this is if lambda equal to nu, or it's equal to 0 otherwise, right? So you can say that, so this term is, so that means instead of this term, तो इसके बदले में देख सकता हूँ, so this can be written as this is delta lambda nu partial x rho partial x square. Okay. Okay, sorry for this intervention. So we have so this is basically our this term, right? Now if you write this now, if you take this variation, if you take its variation now if you differentiate this, if you differentiate this term with respect to the some this primary coordinate, so that means take its variation with respect to x prime mu, right? So that means instead of this term we can write them. So that is partial x prime lambda. So it is so yeah, you can say that so differentiate with respect to x prime. So we need to differentiate it with respect to mu, right? So first term, so that means we need to differentiate this equation with respect to mu, right? So that means you need to take that partial by partial x prime mu. That should be equal to 0, right? Because this is simply that conical delta, right? It's simply constant value, either it can be 1 or 0. So it's simply a constant, so its variation will be equal to 0. So this is very clear to you, right? Now if you have a look on our left hand side, so let us differentiate it partially. So first we differentiate first term, then you differentiate second term, right? So that's it's very clear, right? So you can rewrite this term as that's partial to x prime lambda. Okay, so this is very clear because what I did here, I basically differentiate this term, so that's partial to x prime lambda. This term, तो पहले मैंने इसको differentiation किया, right? So that's partial to x prime lambda, then partial x rho, then partial x rho. I need to sorry, it's sorry. So there is little bit modification here. So we can write here. Okay, so this is clear. So we can write. So that's clear, right? Because rho is here. So this sigma, so this will cancel. So you'll get the same term, and you differentiate it with respect to that x prime mu, right? Now similarly, so this is our first term when you differentiate this term, and this term is constant. Now second term will be, so take this as constant, that's partial x prime lambda. That's partial to x rho. So why I am doing this thing? So because it is very clear why यहाँ पे मैंने differentiate क्यों किया इसको with respect to mu prime, because I should get some affine term here, right? Because we have some that t lambda prime mu nu, so that's basically equal to like this thing, okay? So it will be something like that affine connection, right? Oh, okay, so you can rewrite this term. So if you have a look on this term, so if you check this equation, तो अगर हम ये equation check करेंगे, तो ये term जो है, this term is equal to, so that's partial x prime lambda. This term, so this is same what I obtained here. So this is this thing, right? तो इसके बाद मैं लिखूंगा minus sign this term, right? So that means I can rewrite them term. So I can rewrite them. So equation first I can write as partial lambda prime mu. So that's equal to, that's partial x prime lambda, partial x rho, partial x tau, right? And minus partial x, Okay, so this is what I obtained, right? So this, so we can say that as a coefficients of this affine connection, that is T lambda prime, these are not the components of a tensor, right? So we can say that, so we can write it as like this indices upper and lower like contravariant and covariant, but as I already told you, so these components of this, these are not the components of a tensor, right? But we can write something in superscript or something in subscript, so we can write it that way, right? So we can, so that means we can write this as, so if you introduce here, that is G lambda, or you can write here, so you can write here rho lambda, so this will be equal to tau, right? So we can rewrite it this way because you can multiply by that this Mankow schematic, and so this, so you can have the same kind of contraction like you have contravariant and covariant. You can convert that contra into covariant and covariant into contravariant by multiplying that this Mankow schematic, right? So this is what I did here. So I simply multiply by this whole lambda. So this lambda will contract. So you'll get this thing. So because you can get then tau rho mu. Okay. So that means we can rewrite this. So this I can rewrite in terms of this matrices. So 1 by 2, that is G rho sigma. So we can write it this way, right? Because when you expand this, so by taking this, so you can get the same term, right? Because this partial mu is, so this partial mu is simply that is equal to partial upon partial x mu, right? Or you can take partial mu, so it is, or you can write that partial mu is, that's partial upon partial x mu, and partial sigma, that's equal to partial upon partial x. Okay, so this is very clear, right? Now, so that means I can rewrite this term as, so if you put now, because this, if you put now, this is T lambda, so if you put mu equal to 0 and nu equal to 0 here, right? Because if you remember that in the previous topic, we have already talked about, if you take, because this is a 4 vector, if you take the time component, it will survive, right? What about those space components? Those will be 0. So just check my previous video. So because I am getting those space components are 0 there, right? Only the time components are there, because when you transform like that Lorentz transformation, we have this, we have something like, so if you remember that, if you remember that we are writing that u mu equal to some gamma times c comma v, right? तो वहां पे मैंने बताया था, अगर if you talk about non-relativistic particle means velocity is less than 1, right? So and c equal to 1, so you are getting only the component here. You are getting the u0, then that's equal to dt by delta. And what about these UK components? So those will be equal to 0 for k equal to 1 to 3. So I have discussed this thing in my previous this lecture. So this is very clear there, right? So that means I will talk about that for the time component here. That means that mu equal to 0, nu equal to 0, right? So I can rewrite this term as, so that means I can write that T lambda 0 0. So that will be equal to, so if you put that lambda equal to 0, mu equal to 0, so you are getting there this mu equal to 0, nu equal to 0, right? So mu equal to 0 and nu equal to 0, right? And sigma will contract, so we'll get only one term. So that is basically equal to minus 1 by 2 partial of lambda g0. Okay. So means when you put mu equal to 0, nu equal to 0, only that term will survive. So that is, if you check that, so that's our last term here. So that's our last term. So where is that? Okay. So this term will survive here, right? Because the sigma and sigma will contract, right? So we'll get that 0 mu, right? Mu equal to 0, mu equal to 0. You'll get minus 1 by 2, some partial of lambda, you can say that, right? So this is what I wrote here, that's partial lambda g00, right? Or if you remember that, so this g mu, how it is related with this I00. So that's basically eta mu, plus h00. So that is mu this one, right? So that's basically the height, distance you can say, the vertical distance, right? And this is again that like Minkowski matrix you can. So this is again that the matrix, right? So this is the combination of these two. That is it is a vertical distance plus that eta mu, right? When you put that mu equal to 0, mu equal to 0 here, right? So you can write that tau lambda 0 0. So that will be equal to minus 1 by 2 partial lambda. Okay. So eta 0 0 it will be equal to 1, right? Because so this is like we have this. So it corresponds to 0 0 corresponds to our first element, right? So that's this is what I wrote here that eta 0 0 will be equal to 1 and this will be equal to that is minus 1 by 2 partial lambda that is 0 0. This will be equal to minus 1 by 2 partial h 0 0 partial, right? Or you can write this as now if you take this because if you take that this is partial by partial x, so this is that space. If you take because it is along that x or you take the x, y and z component, so this will be then minus 1 by 2 that's nabla of h0, right? Now if you compare this, so this I can write as, so this is tau lambda 0 0, so that's equal to this, right? Or you can write that plus 1 by 2 that's right, okay? Or so if you compare this equation with the free fall of an object, right? So that means if you compare this with equation that d2x by dt2 minus g that's equal to 0, right? So that means this g will be then, so g is our that's minus 1 by 2 nabla of h, right? So this is simply that gradient of that, right? So that means gradient it tells us that where the variation of this g is maximum. So gradient tells us if you take the gradient of some function, it tells you where the this h where the variation of this h is maximum, right? So you can say that. So this is this simply gives us that that this affine connection or the second order term it corresponds to our the gravitational field, that second order derivative, right? So there is in addition to that, if you talk about now, so there is now another topic that's about if you talk about the covariant derivatives, right? So covariant derivative means if you take the variation of some four vector with respect to some coordinate like x prime here, right? So as I already told you, we have discussed that if you take the variation of some this vector, right? So the or differentiation you can say that. So the new will be some whether you get the new as a vector with the same rank or not. So this is very clear. So if you talk about the plate space time, right? So there so you will get the same this tensor or vector of same rank, get some another vector or tensor but of same rank, right? But in addition to that, if you talk about the curved space time, right? So in that case, we are not getting exactly the different tensor but same rank. You are getting some additional terms. So those terms corresponds to our that space time curvature, right? So this is what basically that second order derivative comes out, and this basically helps us how you can connect. If you make transformation from some moving to some rest frame, so how you can connect them, so that is that you can do by the help of this affine connection. And we already so this is very clear. So when we talk about this Newtonian limit, when you talk about that in the limiting case when velocity is very less than 1, so in that case our that this second term, so that it corresponds to what the gravitational field, right? So in second in covariant derivatives, we will also talk about that if you talk about the motion of an object from one point to another point, right? So in that case, you can see the direction will not change, right? So if you talk about that, if we have some, if an object is moving from some point A to point B, right? So it has some this direction along this direction, right? So you can have same direction. So that means this you will get the same direction will be same here, right? In addition to that, if you talk about the motion of a particle on a sphere, right? So from some point A to point B, right? So if you go from point A to point B, then you come back, right? So direction will be different. So that means the tangent vectors at the 2 points will be different, right? So this is how what we have observed in this space time, because our space is curved here, you cannot get this straight line from some point A to point B. So we'll talk about that. What about the covariant derivatives? So what kind of physics were extracted from that? So hopefully we'll discuss that in coming lecture. Thank you very much.